little bit more some advanced algebra kind of calculating skills, but it deals right with standard form, what we've been talking about, and quadratics, and why do we need graphs of a quadratic? So this is maximizing area. So projectile motion, maximizing area, also maximizing profit are all applications that can be solved with a quadratic. So this situation is you have 500 yards of fence and you have to build a rectangular field. What dimensions should you use so you can get the maximum area? So you could put, you could do a long and narrow one. You could have less on the width and more on the length. So you got to split up these 500 yards. So it says, here's an equation that represents the perimeter of the field. You have 500, right, yards of fence, and a rectangle is always, right, length, length, width, width. So 2 lengths and 2 widths has to add up to 500. And it says, solve for L in this equation, basically to get one of the variables by itself. And then it says, then write a formula for the area of the field. We know that area is length times width from geometry, right? So the area of the field is what we want to maximize. And it says, do that in terms of the width. So L times W, I can't solve that because it has 2 different variables, right? Area equals length times width. But if we could get the area equation with just one variable, we'll be able to solve to maximize for the area. So it says, let's solve for L in this equation. So how would I go and get L by itself? I didn't leave you a whole lot of room. So if I have 2L plus 2W equals 500, what would be my first step to get L by itself? Yep. Minus the 2W to the other side, right? So 2L equals 500 minus 2W, because those are not like terms. Yep, and then what would be the second step to get L by itself? Right, divide everything in the equation by 2. So I have L is equal to 250 minus W. So I just got L by itself. And so if L is equivalent to 250 minus W, I can use substitution and plug the 250 minus W in for L in the original area equation. So then I'll have area in terms of just the width, which you might not have thought to do that, right? So I'm showing you the strategy, and now that you have the strategy, you can apply it to some of these other problems. So my area equation is 250 minus W times W, which is a quadratic equation, because W times W, when I distribute, is going to give me W squared, or negative W squared in this case. So it says, solve for L in the formula. We did that. Step 2, write the function in standard form so that we can identify the vertex. So to put this in standard form, I'm going to do 2 things. I'm going to distribute the W into the parentheses, and I'm going to rearrange it in standard form at the same time, because this is going to give me negative W squared, and this is going to give me 250W, right? So my standard form equation will be negative W squared plus 250W. Would you agree that those are equivalent equations? I just distributed the W, and then I rearranged it kind of in the same step. All right, how do I solve for the vertex? So this is in standard form. So what formula do I use to find the vertex? Yep, so I have to do negative b over 2a. In this case, the c value is 0, because when the width is 0, the area is 0, right? So this is my b value, 250, and my a value is negative 1. So I'm going to take negative 250, because it's the opposite of b, and I'm dividing by 2a. 2 times negative 1 is negative 2, so I get 125. So what is 125? The x value, meaning the width value of my field. Did you get a mask from there too? Oh, good. I wonder if a lot of the masks today are just going to, okay. So we've got 125 is my width. So they wanted just to find and identify the vertex. I guess I didn't find the area yet, right? So 125, comma, what? So use your calculator, plug 125 into the area formula, and tell me what you get for area. So you've got 125, you're plugging it in for this negative W squared, and then you're adding the 250 times 125. So tell me what you get, maybe someone, if you plug in 125. And in this case, you don't need to use a parenthesis because the negative is actually outside of the function. So you just type in negative 125 squared without a parenthesis right there. 15,000, did you get? So it was 15,625. Draw a rough sketch of the area function. This is going to be a concave down parabola, right? So something like that, right? So our vertex is at 125, comma 15,625. So when the width is 125, we get our maximum area. So 125 is the width, and you need to solve for the length. And the maximum area was 15,625 yards squared. So figure out, you could either use the perimeter formula or the area formula. Figure out what the length would have to be to make it true. So you have two W's, and you have two lengths, and they have to add up to 500 altogether. So what's someone get as their length? Or you could take your area and divide by your width, right? Because length times width has to give you your area. So you could do division to go backwards. So wouldn't two W's be 250? And you only have 500 yards of fencing, right? So don't you have 250 yards of fencing left then to do two lengths? So did you ever learn in geometry that oftentimes, well, these should be yards, but oftentimes a square, right, will maximize the area better than a rectangle that has the same perimeter? Did you ever talk about area and rectangles versus squares in geometry? So that is a real thing, and we just kind of figured it out that if we have a square area or square pen, we're going to have the maximum area. And as you stretch out the length and you decrease your width, you're still using the same amount of fence, but your area of your field gets narrower and narrower, so you have less square yards. All right, I want you to try the next example. So it's using the same technique, writing a perimeter formula, writing an area formula, but the pens are a little bit different in example B. Now you have 600 yards of fence, and you're making side-by-side pens, but they're right next to each other. So they're sharing this inner wall. So you have to think about, you've got these lengths of fencing, right? So you're using all of those lengths of fencing to get your perimeter. And then how could you write the area formula? So think about, to get the entire area of the pens, what would your area formula have to be? So take a minute and at least see if you can set up the perimeter and area formulas. I'm going to put those up in just a minute because I don't want you solving it with the wrong formula. But see if you can write a perimeter and see if you can write an area formula for these pens in this diagram. And then once we're sure that we have the right formulas, we'll try to actually solve the problem. So I'll give you a minute to think about this. So for perimeter, you should have said there are 600 yards of fence, right? And I have 3 W's plus 4 L's. And then you're going to need to either solve for W or L. It's your choice. Get one of them by itself. And then what about my area? area is equal to what times what in this case? So I would just look at, if I was going to find the area of this big rectangle, what is the length and what is the width of the big rectangle? So I would have just said 2L times W. So it's a little bit different. It's not just length times width, right? What is the length of this side of the rectangle? That's 2L's and times W. If I do those two dimensions, I'll get this all filled in. So you've got two new formulas for perimeter and area. So try to follow that same strategy that we did up top. It doesn't matter which one you pick to solve for, right? You could either solve for W by itself or solve for L by itself. You're going to end up with a fraction. That's okay. Then whichever one you solved for, you're going to substitute into the area formula. So try to do this step by yourself for a minute. And then maybe before you solve for the maximum area, you want to make sure that your formula is right before you do the whole rest of it. So try to solve for either W or L over in the perimeter formula, and then plug in what you get over here. I'll give you a minute to try it first. All right, so some of us might have solved for W by itself, right? So if you got W by itself, you would have 600 minus 4L equals 3W, and then you divide everything by 3, right? Did some of you take that approach? So let's see, 600 divided by 3 is 200 minus 4/3 L equals W. So U, area equals 2LW. You're going to plug all that stuff in for W in your area formula, right? So we're going to get the same answer. Some of us are just solving for W first, or some of us are solving for L first. Those of you that chose to get L by itself, you would have done 600 minus 3W equals 4L, and you would have divided through by 4. So that would be 150 equals minus 3/4 W equals L. A equals 2LW. And you would have plugged all that stuff in for L in that equation. So you should be on one of those two next steps. So either take this equation further, put it in standard form, or take this equation further and put it in standard form. And then you're just finding your vertex. Once you have L, you're going to find your W, or once you have your W, you're going to find your L. But we should all end up with the same area and the same dimensions in the end, no matter which one we solve for first. Did I lose anyone on getting a variable by itself and then having an equation to plug in? So manipulate it very carefully. This is kind of that advanced algebra kind of step that I'm talking about. You're taking a pretty complicated set of equations to get your quadratic equation. Once you've got your quadratic equation, finding the vertex is the easy part. But you've got to get it in standard form first. One standard form equation if you like that one. And then the other one, I'm taking 150 minus 3/4 W. I'm going to put the 2W out front so I can just distribute it to both terms. So I'd have 300W minus 6/4 W squared, or negative 3/2 W squared plus 300W. Did you get to one of those two standard form equations? And it should come out to a positive dimension because you're taking a negative and dividing by a negative, and you would definitely need a calculator. So this kind of question will not be on Friday's quiz because you need a calculator to do this. But a question like this could be on the test with a calculator. Oh. All right, once you have one of your dimensions, see if you can solve for the other dimension and the overall area. Because you are using 4 of the L's, but only 3 of the W's. So I got the L had to be 75 yards, and W was from my other equation, was 100 yards. So see how if I have 3 W's, that would be 300. And then the 75, if you add up those 4 75s, you get another 300. So it's kind of the idea of the square, right? We kind of divided up things somewhat equally, but it's not a perfect square. It's a rectangle at the end. And then what's the combined maximum area? So 2 length times width will give you your total maximum area. This one might have been a little bit harder than what I would ask you on the test, but I am going to ask you to justify on the test. So even though you know, hey, it should come out as a square, just giving me the area that would be the square doesn't justify that it's the maximum. If you actually have a quadratic and you find the vertex is proving that it is the maximum because the vertex will always be at that maximum point on a parabola. So if it asks you to justify, you can't just give me the correct answer without justifying it. So even if you know what it should work out to in the end, you're justifying using standard form to prove it's the vertex. So what was 2 times 75 times 100? It came out to 15,000 yards squared. So the back page of this I actually like. I'm going to skip. There's 2 examples that we can do as warm-ups the next couple days, but this is a good reminder of an application of projectiles. And there's no equations on this one. It's just looking at the different throws. I think this is hard for you to see which graph goes with which throw. So like throw 3 on the bottom here lands here. If it's easy to see them up top, because they're asking you questions about which graph is which. So then throw 1 is this one, and it goes to here. And then throw 2, I kind of left black up there. So see if you can answer those questions. It shouldn't take more than a minute or 2, but what's the y-intercept? What does it represent? What's the maximum height or x-intercept of some of these different throws? Describe the concavity, domain, and range. So take a few minutes. If you were given a graph that looked like that, could you discuss some of the key features? We get the y-intercept was the starting height, right? So at time 0, it was thrown from 6 feet. The maximum height of throw 1 appeared to be 16 feet, right in the air, the highest. Throw 2's x-intercept, it landed at 45, and so it went a total horizontal distance of 45 feet where it landed. The vertex of throw 3, I was trying to estimate where that was. Did you say it was at 20 or 20? Yeah, it looks like. Did you say 20 or was it this point? I think it was 20. So I estimated it was 20, 12. So the highest point was 12 feet in the air when it was at a horizontal distance of 20 feet. Sometimes this will be time in seconds after the launch. So like it would say at 20 seconds, it was 12 feet in the air. But in this case, when it was 20 yards away, oh, I guess it was yards, wasn't it? Oh, distance in yards. This should be yards. And then It's concave down for all of them. And I said X for that one was between 0 and 45 on the graph, and the Y values were between 0 and 16. Did you say between 6 and 16? Because the reason it actually goes all the way down to 0, even though it starts at 6, it eventually goes below 6, right? So it really fills this whole area from 0 up to 16. So make sure you didn't put 6 to 16, even though the starting height was 6. It eventually goes to 3 feet, 2 feet, you know. All right, so we've got some of those to practice.